Hello everyone, this is Abhishek Mishra from Art Science Classes Keonjhar. So now we are going to discuss regarding indicatrix and interference figure. So before going to indicatrix and interference figure, we will discuss regarding some basic concepts of optical mineralogy like double diffraction, extinction and interference, and then we will go for indicatrix of different type of minerals like uniaxial and biaxial. Then we will cover the interference figures of different type of minerals and what is the use of interference figure, and then the optic sign determination of different type of minerals. Okay, so starting, first one is double diffraction. What is double diffraction? Double diffraction means when any anisotropic mineral is there over the microscope, and there is an anisotropic mineral, so the terms are anisotropic and isotropic. So what is isotropic? Isotropic means the properties of the mineral, different properties like optical properties, refractive index, the velocity of light ray within the mineral. Okay, the properties are same in all directions for a mineral, so that is isotropic. If that is different in different directions of the mineral, that is anisotropic. Okay, so whenever light ray enters an anisotropic mineral, what happens? It will split up into two rays. One is continuing the same path as the previous ray. You can see here this ray is continuing the same path as the previous ray, and another one is deviated. From its path. After removing from the mineral, after going away from the mineral, they are parallel in propagation. You can see here also, if this is the mineral, this light ray enters the mineral here, this is unpolarized light ray, so here comes a term polarized. So what is polarized? We are going to see that. So when an unpolarized light ray enters an anisotropic mineral, what happens? One ray or one component of that ray, it splits up into two components. One component that continues the direction, that continues in same direction as the previous ray. Another one is deviated and then continues. So both of them are parallel. The vibration directions are perpendicular. The migrations are parallel and vibrations are perpendicular. So what is vibration? Whenever a light ray is moving in this direction, let's consider this is west to east, so direction of propagation is from west to east, but direction of vibration means the vibration of molecules of the medium, right? The light ray is not vibrating. When light ray passes, light ray is an energy, okay? When it passes through the medium, the particles of the medium, those are going to vibrate. So these are vibrating perpendicular to the direction of propagation, and that can be in any direction. If this is the light direction, if this is the direction of propagation of the light ray, the vibration can be like this, can be like this, can be like this, anything, infinity, right? Infinity number of vibration, but those are perpendicular to the direction of propagation. So we are denoting the light ray vibration as sine curve. You can see that is like sine curve, okay? All of equal amplitude. Okay, so that is represented as sine curve. So that is the light vibration, and that is in many directions. So whenever a light ray that enters a mineral, the mineral is having some specific property to allow the mineral with a single vibration, right? Before entering any mineral, the mineral is having many vibrations. When it enters a mineral, we are going to see in next slide. When it enters a mineral, what happens? After removing away from the mineral, it will have single vibration. So here it is polarized, and before that, that is unpolarized. When that is vibrating in many plane, then that is your unpolarized. When that is vibrating in a single plane, that is polarized. So what happens when a light ray, unpolarized light ray that enters an anisotropic mineral, it splits up into two rays. One is ordinary, one is extraordinary. Ordinary means the ray doesn't have the name of ordinary. It is given the name, or it is given the component. Okay, that is the ordinary component. So why it is named as ordinary component? Because it obeys Snail's law. And and as I have told that it has continued the same path. Okay, so Snell's law, what is Snell's law? Sin I divided by sin R is equal to mu. That means sine of angle of incidence divided by sine of angle of refraction will be a constant. So the ordinary ray that obeys the Snell's law, so that is ordinary, and it is extraordinary because it doesn't obey the Snell's law. Okay, so that is extraordinary ray. So whenever light ray enters the mineral, it splits up into two components, ordinary and extraordinary. Ordinary obeys Snell's law, extraordinary doesn't obey Snell's law. Ordinary continues the path, extraordinary deviates from its path. Then both of them are parallelly migrating but vibrating perpendicularly. The vibrations are perpendicular. You can see here, if this is the vibration of ordinary, this is the vibration of extraordinary, right? So this is known as double refraction. This is known as double refraction. Single ray enters the mineral and removed as double rays or double component. So you can see here, this is the unpolarized light ray that enters the mineral. Here it is calcite, here it is calcite. When it enters the mineral, what happens? One continues the same path, another one is deviated from its path. Then both of them are migrating parallelly. Both of them are migrating parallelly, you can see here. Both of them are migrating parallelly, but the vibrations are perpendicular. You can see here, it is vibrating parallel to the board and it is vibrating towards the board. That means inside the board and outside the board, right? So both of them are migrating in a parallel direction but vibrating perpendicular to each other. Okay. So this is your double refraction. Then we will go to polarization. So you can see here unpolarized light ray. Whenever talking about unpolarized light ray, there is a single direction of vibration, single direction of migration, but the vibration is in many directions, that is perpendicular to the direction of propagation but can be in any direction. Okay, so this is for unpolarized light ray. When it enters through a polarizer and removes from the polarizer, it will have a single plane of vibration. You can see for both of the case, the direction of propagation is this one. The direction of propagation is same, but just the vibrations are reduced to one plane. You can see here the example of tourmaline crystal. This is tourmaline. So every mineral is having its own vibration direction. Okay, whenever the light ray which is unpolarized, that means you can see here it is vibrating in many directions. It enters the tourmaline crystal, it removes from the tourmaline crystal, its vibration is in single direction, and that vibration direction is defined by the vibration direction of the tourmaline crystal, which is parallel to c-axis. For tourmaline crystal, the vibration direction is parallel to c-axis. So it allows the ray only to vibrate in that direction which is parallel to its c-axis. Okay, so that is polarization. Similarly, we are talking about calcite. We are using calcite as polarizer in microscope. So calcite is also a polarizer. It is having two vibration directions. When before this slide I have discussed regarding double refraction, so ordinary and extraordinary. Talking about those rays, those are partially polarized. Whenever that light ray splits up into one ordinary and extraordinary, both of them are partially polarized. If we are using calcite as a nickel prism, right, there is some coating, black coating is there. I will discuss that how nickel prism works. But there it allow only one ray. So both of them are partially polarized. One is remain there and observed in the black coating, and another one is removed from the calcite. So that acts as a polarizer. Okay. Now talking about what are the phenomena occurring in an optical microscope. So we are going to study optical mineralogy, means before that we should know what happens in microscope. So see here, if that is a unpolarized light ray, here it is the stage, here it is the stays, right? Nothing is there, no polarizer is there, no analyzer is there. What happens? The light ray pass through the stays, there is no mineral. Here it is, no mineral. So the unpolarized light ray we can see as unpolarized. It is vibrating in many directions, so we can see white light. Okay, we are providing white light here below the source. Before there is previous case the microscopes are not having any source. There is a reflecting mirror, right? The sunlight falls on the reflecting mirror and reflected back to the microscope. So then that's why it is known as reflected microscopy. Okay, so here in that case we are using reflecting mirror, but nowadays the microscopes are provided with own source that is present below the stays, right? Here it is the illuminating the source, it is the source of light here. Okay, in previous case there is a reflecting microscope. So what happens, we are providing white light, that is unpolarized light, and if there is no mineral in the stays, we can see the unpolarized light ray and white ray. Okay, same way we can see. If there is a polarizer, you can see this is a polarizer. You can see the fixed vibration direction or fixed orientation of vibration of the polarizer, that is from west to east. Okay, the polarizer is having its fixed orientation of vibration, that is from left, right or west to east. Okay, when the unpolarized light ray enters the mineral, enters the polarizer, what happens? You can see it is vibrating in only that direction which is parallel to direction of vibration of polarizer. Then what happens? If I will insert an analyzer, okay, it is the polarizer, it is analyzer. So what is analyzer? Analyzer is another polarizer. Analyzer is another polarizer, but that is used above the stays. Polarizer is used below the stays to polarize the light ray, then it falls on the mineral. Here there is no mineral. You can see here there is no mineral. Stays is obviously there, but there is no mineral is placed. Okay. Over that there is an analyzer. Analyzer is itself a polarizer. Both of them are nickel prism. Both of them are nickel prism or calcite. Okay. So what happens? The polarizer and analyzer, they are having mutually perpendicular direction of vibration. You can see this is having left to right or west to east. This is having north-south vibration direction. So both of them are perpendicular. So you can see the light ray that passed through the polarizer, that is having a vibration of west to east. But the analyzer, it is having a vibration which is perpendicular to the vibration of light ray. So it doesn't allow the light ray to pass through it. Okay, in this case, in case of polarizer, the light ray is vibrating in many directions. So there is a direction parallel to its axis or its vibration direction. That's why the ray removed as that direction. But in this case, the analyzer is allowing the light ray which is vibrating north-south. But here there is no north-south component. So that cannot remove from the analyzer. So we can see the darkness in the microscope, but we are naming it extinction. But here there is no mineral. If we will put mineral, then we will show other condition when there is extinction, when there is interference. Okay. Now let's see if I am entering a mineral here. Right? You can see here I have entered a section here. Okay, that is unpolarized in previous case. Now I have entered the mineral. So the mineral is anisotropic. It should be anisotropic. If it is isotropic, then what happens? The same thing will pass through it, because there is no change in properties in every direction. So the same ray that will remove from the isotropic mineral, and again that same thing will happen. It will not pass through the analyzer, and there will be darkness. Whenever there is anisotropic mineral, what happens? That ray again, so double refraction, it will split up into two rays, one ordinary and one extraordinary. Okay. Now this both ordinary and extraordinary, that again enters this analyzer. What is within the analyzer? Calcite. Calcite is there. Calcite is an isotropic or anisotropic? Calcite is an anisotropic mineral again. So what happens? This O ray and E ray that again enter the calcite. Again this O ray splits up into one ordinary and extraordinary. Got that? That's why I have told in previous case, ordinary, extraordinary, that is not a name. That is a component that is given according to their behavior. Okay. So this ordinary ray which enters the calcite, which is an anisotropic mineral, that again splits up into ordinary and extraordinary. Extraordinary ray that enters the calcite, that is again divided into ordinary and extraordinary. Got that? They are different rays. This different ray when enters the anisotropic mineral calcite, they again divided into 4 rays. 2 rays they will give to 2 rays each. Okay, 2 rays they will give 2 rays each. That means 4 rays. Then what happens in calcite? What happens in nickel prism? Nickel prism is like this. Here it is. The Kannada balsam is there, the calcite is caught in between, and it is the Kannada balsam. Here this angle is nearly about 71 degree, right? When a light ray enters through the calcite mineral, what happens? One ray pass through it, one ray deviated like this. Then here Kannada balsam, there is a difference in refractive index between Kannada balsam and the calcite mineral. So what is the refractive index for Kannada balsam? 1.54. Okay. What is the refractive index for calcite? 1.4. Right. So what happens when the O ray, when the refractive index for calcite, that is for different rays, right? For ordinary it will have some refractive index. For extraordinary it will have some refractive index. Got that? For the mineral, the refractive index is defined for 2 different rays, right? For calcite, the ordinary is having some refractive index, and extraordinary, that is having some refractive index. So extraordinary, I think that is 1.6, or that is I think ordinary is 1.6. Ordinary is 1.6 or extraordinary is 1.6.
Extraordinary is 1.6. Very slow.
See, here it is, the phenomenon is occurring total internal reflection, right? Here there is total internal reflection. Total internal reflection requires the movement of light ray from denser to rarer. From denser to rarer. So ordinary will have more because it passed from denser to rarer medium. So ordinary should have 1.6 and extraordinary should have 1.4. Okay. So Kannada balsam is having 1.5. Ordinary when enters from calcite to Kannada balsam, it passed from denser medium to rarer medium. Because in calcite its refractive index is 1.6. and in Kannada balsam its refractive index is 1.5. So it is passing from denser to rarer medium. Then what is total internal reflection? You can see this is denser, this is rarer, this is the normal. When light incident on that surface, what happens? The angle of refraction will be higher than the angle of incidence. R is greater than I. Why? Because it is denser and it is rarer. Okay. So when it continues with increase in angle of incidence, at certain angle it will pass through the interface. At certain angle, because if I will increase angle of incidence, the angle of refraction will increase. So at certain angle of incidence, the angle of refraction will be 90 degree, right? Here I is equal to C. That means critical angle. This is the critical angle. When I is greater than C, when I is greater than critical angle, then what happens? It will suffer critical reflection. That means the ray will reflect back to the same medium instead of going to other medium, right? So that occurs when there is movement of denser to rarer medium. So when ordinary ray that travels from your denser medium, that is calcite, to rarer medium, that is Kannada balsam, so what happens? It will suffer internal reflection or total internal reflection. Okay. So ordinary ray that comes back and absorbed by the black coating here. Here it is, black coating is there to absorb the ordinary ray. Only extraordinary ray that can pass through the calcite. Only extraordinary ray that can pass through the calcite and remove from the calcite. So this is the mechanism of polarization in case of nickel prism. So let's come to our topic. Yes, so analyzer is calcite crystal, that is anisotropic mineral. So what happens? There is two ordinary rays. There are two ordinary rays and there are two extraordinary rays. So what happens? Both of the ordinary ray, they will not pass through the analyzer. They will not pass through the analyzer. So which ray will pass? Only extraordinary. Only extraordinary ray will pass through the analyzer. Then the interference between these two extraordinary rays, they will show us color. Okay, so this is the phenomenon whenever we are talking about a single wavelength of light. Single wavelength means monochromatic, right? Monochromatic means mono means single, chrome means color, one color means one wavelength, right? So whenever we are talking about a single wavelength of light, that means let's say red, let's say green, blue, anything. So one wavelength that will go produce two extraordinary rays after the analyzer. So what about the seven wavelengths that is constituting of white light? White light is having 7 wavelengths, right? So for 7 wavelengths, it might produce 14 wavelengths, 14 E rays, right? So in each mineral we can see same color. But I am asking a question, whether you can see same color for each minerals, because all of them are producing 14 E rays. So you can see each mineral with same color? No. Then what is the phenomenon in behind that? What happens? The mineral is having certain vibration direction. I have told you, every mineral, every anisotropic mineral, that is having certain vibration direction. Okay, that vibration direction is having a resultant. Okay, that vibration direction is fixed for a fixed wavelength. If there are 7 wavelengths, the vibration direction is constant, the refractive index is constant for certain wavelength. So there will be two vibration direction and there will be a resultant. There will be a resultant depending upon the retardation. What is retardation? One ray is moving faster, one ray is moving slower. So there is some path difference. There is some difference in path, that is retardation. There is some difference in refractive index, that is known as birefringence. So these properties define which ray will be coming out of the analyzer. That properties, the retardation and the birefringence, both are related, right? Retardation is related to birefringence. That property that property correlate, or that property define which light ray that will enter the analyzer and can remove from the analyzer. Okay, these two extraordinary ray, that is not for all 7 wavelengths for each mineral. Okay, if there are 7 wavelengths coming out of a mineral, you can see white color. Okay, but this property, this retardation, this birefringence, this difference in refractive index for ordinary and extraordinary ray for different mineral, that is different, and that defines which light ray is going to pass through the analyzer, whether that will interfere or that will extinct, whether that will interfere or that will extinct. If that will interfere means some light ray can be passing through the analyzer. Extinct means all of the light ray, they are behind the analyzer, they cannot pass through the analyzer, right? All of the 7 rays, they are not 7 wavelengths, they are not passing through the analyzer. Okay, for interference, what will happen? If the light ray will go out of the analyzer, if the light rays they are going out of the analyzer, then how much intensity and what are the wavelengths? Not in all case they are 7 wavelengths. Not in all case they are 14 E rays coming out of the analyzer. They can be 14, they can be 12, they can be anything, right? So that depends upon this property of mineral. What is the birefringence, what is the retardation? Okay, so that depends how much rays or what are the rays they are coming out of the analyzer, and that depends if they will interfere, what color will produce by the mineral. That is not the actual color. That is where defining the interference color. interference color, right? If we are talking about interference color, we are writing in the definition that it is a false color. It is not the true color of mineral. The true color of mineral is different. But this false color is produced due to the selective appearance or selective passing of the rays from the analyzer. That depends upon the properties of mineral. Got that concept?